Hi, everybody. I want to catch up with you here on chapter 13. Start doing some problems, working through some things. Hopefully, you've looked at the chapter 13 videos that I've put out there for you on three-phase induction motors. And now I want to go through a little part of, I want to present 5 equations to you. And if you can know these 5 equations, you can really do a lot of work with three-phase induction motor calculations. All right, so here you are now, right? You should have this fundamental idea of how a three-phase induction motor works. We supply 3 phases, 3 different voltages to the stator. They're 120 degrees out of phase. Okay, so there's this natural rotation that occurs, this rotating magnetic field that's occurring in the stator. This rotating magnetic field induces voltage in the rotor. Currents start to flow. Once current starts to flow, it creates its own magnetic field. There's an interaction with the magnetic field of the stator, the magnetic field of the rotor that's induced. And so what happens is this interaction causes the rotation of the magnetic field in the stator to actually drag the rotor along with it. So you get these, this situation of induction, and it's how we convert electrical energy into mechanical energy, and the magnetic field is the medium from which that happens. So now what we want to do is start to quantify this a little bit. And so I'm going to present five equations, and not saying you need to memorize them, but they should be sort of second nature to you in your understanding of how a three-phase induction motor works. So let's look at these. So here are the 5 equations, and I think they actually are, they're given in the same order in your textbook. And so let's just walk through these, do a few examples. The first one's sort of the fundamental equation for three-phase induction machines, where the synchronous speed, Okay, now let me emphasize a couple of things to you here. Now, when we talk about the synchronous speed of a three-phase induction motor, we are talking about the speed of the rotating magnetic field that's established in the stator. It's given a designation of N sub S, and the way that that's calculated is that it's 120 times the frequency of the source. Most of the time that's going to be 60 hertz. Sometimes you'll see 50 hertz, depending on the location. European standard is 50 hertz. We look at 60 hertz in the United States. And then the number of poles of the motor. Now, our textbook uses, number of poles, doesn't use pole pairs, don't want to get into that confusion. And so this gives us the synchronous speed of a motor. So that allows us to work problems such as example 13.1, where it says that calculate the synchronous speed, N sub S, of a three-phase induction motor that has 120 poles. 120 poles. That doesn't even seem practical, and it's not. It has 20 poles and is connected to a 50 hertz source. All right, so we jump right into one of these that, is not 60 hertz. So the frequency is 50. The number of poles is 20. This is not a commonly occurring motor. A 20-pole motor would be very expensive to make just because of the complexity of it. But anyway, so 50 times 120 is 6,000. 6,000 divided by 20 is going to be 300 RPMs, okay? So this motor, synchronous speed, the magnetic field is going to rotate at 300 RPMs. Now, that doesn't mean that the motor rotor is actually going to turn at 300 RPMs. It just gives us a value for the synchronous speed, the magnetic field speed that's rotating within the stator. Okay. Now, so that's a fundamental, something that we should be able to use. Sometimes we might be given a problem, and it might say that the I don't know. It might say that the synchronous speed is, say, 7,200, and we're being supplied by a 60 hertz source. So I'm going to write that in here, and I'll just put 60 hertz. And maybe we're asked to figure out how many poles are in that motor. All right. So a problem like that, then we're going to solve for poles, and we'll multiply both sides by P. We'll divide both sides by 7,200. And we could get an answer, that way. So it depends on what they're asking for. Sometimes you might calculate the F, but of course you'll be given all of the values that you need to be able to calculate a particular value. All right. Now I'm looking at this one, and I think that when I did this, it didn't really make any sense, does it? Let me clean this up a little. Let me try something else here. Let's say that instead of 7,200, we'll actually do a problem here. Let's put I should have put a different value here. Let's say it's 1,800. It's the synchronous speed of the rotating magnetic field. All right, I'm going to calculate this for the number of poles. 60 times 120 is 7,200. This number comes up a lot, guys, because most of the time it's 60 hertz. So 60 hertz times 120 is going to give us 7,200. We're going to divide both sides by 1,800, and then 72 divided by 18 is going to give us 4. So this would be a 4-pole motor. So, those are the kind of calculations that you're going to do using equation number 1. All right, now let's look at the second equation. Okay, the second equation is a calculation of what we call motor slip. This is a common term in relation to motors. It's a fundamental understanding. It's a concept in relation to motors. And so let's kind of walk through this. And, again, hopefully by now, you've already seen the videos, where the textbook is going into these very good explanations on this. But let me just point out a few things and talk to you about that. So there's the motor slip formula. And it says slip is a value that is calculated by taking the synchronous speed that we just calculated in 13.1 and dividing or subtracting from the synchronous the rotor speed. They're never the same in a 3-phase induction squirrel cage motor. And so there's this difference. And then that difference is divided by the synchronous speed to get this slip value. Okay, now the motor slip is an important determination for a 3-phase induction motor. We would do this in the lab. I hope we get the opportunity to do this in a lab. And the way that we would determine what the motor slip is we would use something called a strobe tachometer, and we would actually, physically determine what the rotor speed is and calculate what the synchronous speed is by knowing the number of motor poles and the frequency of the source. So what I might have, an example of something like this to determine what slip is. We can find this in our textbook on page 274. And, you might have some information like given to you in example 13.2, where it says you have a half horsepower motor, which really doesn't have anything to do with our calculation, right? But, it's given to us. It says it's a half a horsepower motor. It has 6 poles and it's excited by a 3-phase 60 hertz source. If the full load speed is 1140 RPMs, calculate the slip, okay? So the 1140 is a reference to how fast the actual rotor is turning. So I've got everything I need. The equation says slip is equal to synchronous speed. So I can take my information and go back to equation 3.1, 120 times 60, because it's 60 hertz. It's 6 poles. 60 times 120 is 7,200 divided by 6. And so the synchronous speed, the nth of S is 1,200. So now I can plug in the nth of S is 1,200. The actual rotor speed is given to us as 1140. And then we divide that by 1,200. And when we do that, we end up with 11, 20, the difference, and comes out to be 60 divided by 1,200. And that would be 0.05, or I might write that as a percent, and I'm going to write that as 5%. And the way I'm going to say that is that this 3-phase induction motor has a motor slip of 5%. That's a common value. It's a reasonable, realistic value for a motor that's at full speed. And, those are kind of the values that you should see when you're looking at a 3-phase induction motor. Now, let me share something with you, and this will be some of the problems that you'll run into. Now, one other thing I want to point out to you. Sometimes you may be given a problem to where you can use the slip formula to determine the number of poles in combination with equation 13.1. The way that would work is, you have to think in terms of something, and let me just point this out right quick. Let's go to this problem right here. So if we're told that the rotor speed is 1140 RPMs, and a question might be asking you to determine the number of poles, okay? Well, to do that, you got to remember that poles always have to be in multiples of 2. You can have a 2-pole, a 4-pole, 6-pole, 8-pole, 10-pole, and so forth and so on. So if I'm given 1140, and I know that the slip, it's always going to be, a small number. 5% is sort of a normal value for a motor slip. So if I'm told that the case of this, it's like 1140, then what you have to do is, you could actually take your 1140 and you could plug that into your formula for synchronous speed, right? And say it's at 60 hertz, and you want to know the number of poles, okay? And so 1140, 7,200, number of poles, Solving for poles, I would get 7,200 divided by 1140. Okay, well, we know that's not going to come out even, but what we can do is we can deduce that 7,200 divided by 1140, it comes out to like 6.3, 6.3. So what you have to do is you can't have partial poles. So, you wouldn't say it's 6.3, but you would say it's a 6-pole motor. Then you could go back and you could plug that into this, right? You could say that's 6 poles, and this would be 1,200, right? And then you would see that would make sense. Okay, so sometimes those kind of problems come up. All right, now let's look at the third equation. Okay, for the third equation, it says 13.3 F sub 2 is equal to S times F. Okay, all of these, it starts with number 1, usually synchronous speed, usually goes into 13.2 with slip. And so what I'm saying here is F sub 2, which is an indication of the frequency of the voltage and the current in the rotor. And of course, F is going to be the frequency of the source, okay? And S is going to be slip. So that allows us to do yet another kind of a problem that we can determine what the frequency of the voltage and current in the rotor would happen to be. Now, those will always be the same. We don't get into frequencies, differences in voltages and currents when we talk about 3-phase induction motors. So I could have a problem to where, like in the example that's given in 13.3, and say that the synchronous speed is 1,200, and you're trying to determine what the frequency of the induced voltage in the rotor would be. And so, as you walk through a problem like that, as you walk through that problem, you're going to have to start with determining what the synchronous speed is first. Okay. So, for instance, let's say that we went through and we're told the synchronous speed is 1,200, and we use a strobe jack, and we find out that the rotor is rotating at 500, and then so we determine that the slip is equal to 0.583. Okay, now that's a large number for slip, but remember what we really think about. We think about slip when it's at up to speed, at operating speed. So this is somewhere in between that. But then I could take that value for slip and I could plug it into this equation to calculate what the frequency of the voltage and the current would be. So if the slip was 0.583 and the frequency is 60, then I could determine that the frequency in the rotor, in the rotor for the voltage and current would be 35 hertz. Important thing to know there is that the frequency of the voltage and the current in the rotor and the frequency of the voltage current in the stator, they're going to be different values. Okay. Now, that example 13.3 that I go over in that lecture for that, very important problem. Make sure that you understand that. Then 13.4 gives us another fundamental equation that we could use to determine what the voltage induced in the rotor at a particular slip would be. And it's based on the open circuit voltage induced in the rotor at rest. Okay. And in this, it says, it goes into a little detail The open circuit voltage is a voltage that would be induced if the rotor bars, in the rotor bars, if the bars were disconnected from the end rings. Okay. Now that's a little particular detail in there, but again, that would be something that we know what that's going to be, and that's just a little extra detail given to us to determine what the voltage is in terms of in the rotor at a particular slip. And sometimes we might need to know that. And then the last equation here, neat equation, it gives us a way to estimate the full current, the full load current. And what that means is if you have a 10 horsepower motor and you want to know what the current would be when it is supplying 10 horsepower, then this equation gives us a very reliable estimate of what that would be. Okay, and so that's a really useful equation. It relies heavily on that section 13A, the typical characteristics, and so we can get a really good estimation of what the full load current would be. One thing I'd point out with this equation is the use of output power and horsepower. And most of the time we're going to stick with SI units, and we would be talking about watts or kilowatts, but for this particular equation, it references in horsepower. Now, the reason I wanted to make this video and get it out to you is so that you can access this, and I'm going to make a little separate module on this, and you can access these 5 equations. I'm going to supply some problems to you that I want you to work out and submit, and all of them can be basically determined by simply using these 5 equations. All right, and again, the utilization of these equations will help you in understanding how a 3-phase motor, 3-phase induction motor works.